Hey, Matt.
Hey, Mike.
Let's do the podcast.
Okay.
Welcome to Hacking the Grepson, where we try really hard to do a new intro each time, and then sometimes I'm just like, just say the words, Mike. Just move on. I don't need to make a joke or be cool or anything.
I feel like we could have come up with something more complex or that took more time in particular for this episode, but
No,
why?
I mean, no, this is just an array, and I just want to find one index. I just want to get there. I don't want to think about it.
All right.
No.
Well,
So if you couldn't figure out from our witty banter, today we're talking about big O notation.
did you just reference Office Space?
No. Yes, I did. So big O notation. I don't know what that is. What is that, Matt?
It is a way of referring to the complexity of an algorithm in computer science, right? So
Wait. What's an algorithm?
how would you describe an algorithm? It's when former vice president dances. Old joke. An algorithm is really just a piece of code that does something, right? Like if you want to boil it down, like a function could be an algorithm, but generally speaking, you're trying to solve a problem, a complex problem, and you need to do some series of operations to make that happen, right? So if it's if you're doing some math-based things, you might have, some complicated math stuff that you want to figure out. Like I think I've talked before about how you can sort of compute the square root by just adding odd numbers together. Right. Like that.
What about just like an array of random numbers and find the biggest one?
Yeah. So even something like that, it's anything you want to do. So find an item in this thing, and different data structures have different complexities to them naturally. Like it's part of it. And we can go really complex, but we're not going to. Like there's like big theta and other things that like bound the problem a little bit more. But in general, big O
You're in big theta's pocket.
Yeah. Big O is the worst case scenario, like with the worst input, how long is this going to take relative to the size of the input, right? So typically you say big O of, and then it's some function of n, right? So if it's big O of n, that means it is directly proportional linearly to the size of the input, right? So if you were, going to print an array, that is big O of n, right? Because every operation you're doing on it is a constant. It's print. It's the same thing. But if your array is 1,000,000 items long, that's going to take significantly longer than if it's 100, right? But then you can compare that to other ones that take more time or even less time, depending on what you're doing. And that's where, really, that's the meat of computer science as a science, is the complexity and the analysis of all that stuff.
So let's just go back to big O of just n, because that's like the simplest example. You say printing and so you use kind of the example of like printing a one-dimensional array, i.e., like you have an array of the numbers 1 through 100. So you have 100 things in there, and you want to print them all out to the screen. So you write a thing that says, loop through this array and print each item,
or even
or
even adding them, right? Like anything that you're doing, if you only have to go through the array one time, right? That's big O of n. But you have to go through it all. Now you could, so like there's searches that can be big O of n. Like if you literally like, I want to go through this array and find the number 42 and figure out what index it's in. That's big O of n, right? It might be the first index and you pop out and it's 1, but it could be the very last one, or it could not be in there, in which case it's going to be the size of the array. And that's why we don't tend to talk about average times, although that is a worthwhile conversation, and there is a whole computational complexity thing about that I don't think we'll get into here. Because honestly, it's not something I pay much attention to. Generally, you care about the worst case scenario.
Okay. So that's like a big O of n. What's another kind of big O?
Well, before we move off of big O of n, I feel like that's probably the most common one that we encounter as developers, right? You when you write a while loop or a for loop, chances are good you're doing big O of n in that loop is that, right? Unless let's say you have a second for loop in there, right? For I from 1 to 10 and for j goes from 1 to 100. Well, now you're not just going up that 10 in the I, you're going 10 times j, right? And if both of those are for some reason based off of n, so like let's say n was 100 in both cases, just to make this easier. Like you got 100 loops that are doing 100 loops. So you've got 100 times 100. So you've got quadratic time. So that's big O of n squared because it takes you pass it in. If you map out the time, and this is really how you do this, right? You take an algorithm, you run it with a given size of input, and you measure the time. And then you bring the size of that array up. So let's say you run it with 10 items, run it with 100 items, run it with 1,000 items, measure that, and then you graph it, and you can see, like, oh, this is a quadratic one because it does like a, oh my God, what are those called? Like a parabola type thing. Or it's, it's a straight line that goes up. All right. It's
so is that O of n?
That's
the straight
O of n,
line?
is the straight line. If it's a straight line and it's flat, that's constant time. That's big O of 1. Now, I should point out, these are not, it's going to take exactly n things, right? So, for example, there was an interview question that I asked someone today, and their solution for it involved going through the list twice. So that's 2n. But you ignore the constants in that situation, and you just say it's because you're talking about what it's proportional to. So it's proportional to the input. The fact that it goes through twice, it's going to do that regardless of the size of n, but n is the thing that's going to make it take a lot longer or less time. And then n squared, bad. You tend to want to avoid that. And then it gets into things like exponential, where you have like 2 to the n, and it gets worse than that. I'll stay focused on like the main ones today.
Okay.
Which is the main ones that we encounter on a regular basis. And I'll give an example of each one. Constant time, an array index lookup, right? You've got an array, you want index 4 of that array. Your computer just knows how to do that. It says, okay, memory location plus size of thing times 4, basically. Give me that. It's a constant. Lookups from a dictionary or hash table, whatever you want to call it, hash map. That's constant time. And that matters when you're doing things that take a while, right? Or that have big input. Advent of code starts to really matter with those kind of things. Like if you're doing a ton of reading but not a lot of writing, something like a hash map is great, because while it might be big O of n or something for inserting, it's constant time for lookup, right? Linear time, big O of n. Well, okay, I skipped one. Logarithmic time is like the next best after constant time. There are other ones, but they're less common. Log n tends to be used for pretty much like one algorithm. You see it, which is binary search, which is one of the biggest ones, right? You can get things in significantly less time if you can do them in log n than if you do them in n. And if you graph a logarithmic function, you can see exactly why. Because it doesn't continue to go up forever. I mean, it does, but it has an asymptote, basically. And so things slow down. So you see this a lot anytime when you're like dividing the problem in half and then doing something and then dividing it in half and then dividing it in half. You end up with log n. Then you hit linear, right? Big O of n. And that's, we talked about looking up an index in an array. That's constant time. But if you had like, say, a linked list or something where you actually have to go through each one to find the next one. So a linked list, you'll have like your object and a pointer to the next item in the list. So you can't just randomly access an item. You have to start at the beginning and walk your way through it. That's going to be big O of n. That's a very common one. Anytime you throw in a for loop, like I said, you're at least going to have big O of n because of that for loop.
It's almost like the difference between going through an old cassette or VCR tape,
yes,
versus current, where you can just go to any time code in a video file.
Yeah, Yeah, CDs let you do random access. Tapes require linear access. Just to date myself, I didn't use any of the things that we use nowadays. After big O of n, again skipping some, but from like the traditional things that people are generally going to see is big O of n log n. Now this one is usually a combination of the logarithmic time times the size of the array. So you end up with like n times log of n. And this one is worse than linear, but it's not as bad as quadratic because it kind of tapers off. So if you have a huge data set and your choice is, okay, I can do 2 for loops, or I can do like a for loop and then a binary search inside of that, right? You're going to do it n times, you're going to do n binary searches basically. You got n log n. And that's pretty good. If you do a sort algorithm in almost every language, like the built-in sort algorithm is n log n. It's a very, very common time for sorting. Python's does it, JavaScript's does it. All the ones I can think of, honestly, do it. But those are the ones I use the most. After that, you get into quadratic, which is typically like if you were going to search through a 2-dimensional array, or a lot of the less effective sorting algorithms or less efficient sorting algorithms that are maybe more intuitively obvious, run in quadratic time. So that's something like where you're like, okay, I'm going to start at the beginning of this list, and then the first item, I am going to go find where that belongs. So I'm going to iterate along the list until I find where it goes, and I'm going to put it there. Now I'm going to go to the next item in the list, and I'm going to do the same thing. So you're like potentially going through all n items n times. Brute force algorithms, which is usually the first thing that occurs to anyone on like, how do I solve this problem, tend to be n squared. And you get bigger than... Go ahead.
Is that also... Because anytime we talk about brute forcing and that particular O of n, I think of that advent of code, the lanternfish from 3 years ago, where you basically you have a bunch of lanternfish and their timers like go up every day and then they flip over, and then you have to figure out like after a certain number of days what is the final count of fish, like which ones have died, how many have been born, et cetera, et cetera. And me not doing a lot of this kind of stuff in my career probably did the quadratic brute force search, which is why it was just running forever and ever and ever until I figured out that I had to do a more efficient.
I think actually that particular one was exponential, which is the worst I'm going to talk about today.
Oh, okay. So even worse than that. Excellent.
So after quadratic, and I always mix up quadratic and exponential, but quadratic is big O of n squared, and you have cubic time and other ones. So polynomial time basically is sort of the generic one of those. And when we talked about, go back to our P versus NP episode, polynomial time is like, that's good. It's not great, but it's good. It's solvable. If something's running in polynomial time, you're going to get there eventually, right? If it's running in exponential time, like 2 to the n, that's where you start to run into like, this is never going to finish.
Yes.
Even for like relatively small values of n, that grows really, really fast. So those are the main ones. Just to reiterate, we got constant time, big O of 1, linear, logarithmic time, big O of log n, linear time, big O of n. What do they call n log n? Line arithmetic time. I've never heard that before, but big O of n log n. Quadratic, and then exponential. And I'm skipping a ton. But those are the ones
I'm looking at the wiki. There's so many.
Yeah, those are the ones I actually have encountered on a regular basis in the last like 25 years.
Ooh, the one that's bigger than exponential is factorial, like the traveling salesman problem, which is like,
or computing a factorial, right? So actually, that's
right,
a great
which
example.
Is what that is.
As long as we're there, like factorial time, which yes, I have run into that. That's basically big O of n times n minus 1 times n minus 2 times right. It's that long because that's how long it takes to compute. There are ways of writing some algorithms, for example, to calculate a factorial that you can write in big O of n factorial. If you did a fully recursive factorial function, you can do it really, like it's real small, like lines of code, but it blows up in time really fast. And that's where the science part of computer science comes in, because then you look at something like that and you're like, how can I do this better? Well, if I'm doing the factorial of 10, well, I need to know the factorial of 9 and 8 and 7 and 6 and 5, right? I need to basically know all of those. And so I could say, okay, factorial of 10 is 10 times factorial of 9, and then that one launches off and does another thing and another thing.
Like threading or something?
Yeah, with like threading. Or you could build up the other direction. You start, and you could cache information, or you could start at like 1 times 2 times 3 times 4. Like you just go up, and then you don't have to say, okay, I need this and all of those, right? Because you're trying to calculate them. And it's less, I think I've run into this less with factorials specifically and more with Fibonacci. And the way like calculating a Fibonacci sequence, which is, oh God, it's n plus 1 time. I can never remember what Fibonacci looks like off the top of my head. But you end up with 2 functions that you're calculating there at the same time. And there's often a lot of overlap between them, right? Because if you look at the Fibonacci sequence, you got 1, 1, 2, 3, 5, 8, 13, and so on. And all it is you add the previous 2 numbers to get the next one, right? So if you're trying to work like backwards from a number and like, okay, well, what's the Fibonacci? What's the 100th Fibonacci sequence? You could say, okay, well, it's Fibonacci. It's the 99th Fibonacci sequence plus the 98th Fibonacci sequence. But then those things are both running through basically the exact same calculations at the same time, and that blows up. And so that's where being smart and looking at, okay, well, how can I do this more efficiently comes into play, and you end up with, again, caching is a very common method to solve that problem.
That also came up in Advent of Code,
Yep. Or, so usually the solutions to things like that are caching or working from the other end of the problem, right? We tend to think of things like, all right, I need to know the 100th factorial number. And we as humans tend to work from that direction. But if we're smart, we say, okay, well, I'll just count. I'll just figure that out from the first 100. And so you start from the bottom up instead of top down.
So this is all great. I love this. I will not probably remember this, but that's why Wikipedia exists, because I'm reading it just to kind of, because I wasn't sure what was bigger than the exponential one. That's where I found the factorial one, and remembered about the traveling salesman problem, because that was another Advent of Code, probably multiple times.
And a prototypical example of an NP problem, right? Non-polynomial time. Everything below polynomial time is P. Everything above that is NP, basically.
Yes.
I think there's some gray area around that, but that's basically true.
I was also curious why it was called Big O. Apparently the letter O was chosen by Bachmann. That is the German mathematician Paul Bachmann, who is one of the people who invented these notations, or the description of them, and it stands for Ordnung. So it is a German word meaning the order of approximation.
Oh, yeah.
So there you go. Big Ordnung.
Yeah. The layman's term for this is ballpark, right? Give me a ballpark of how much that's going to be. When you say that, you're like, okay, well, what's the computational complexity? And that brings up the other thing, right? Is we talked about all that from a perspective of time, but that same concept of Big O also is true for space, right? So how much space are you using? So a lot of when you're trying to solve problems, a lot of the times you can make a trade-off between, okay, I can do this really fast if I can take up a lot of space in memory, or I can do it slower and not take up any space, right? That is a very common trade-off, especially in job interviews. That is a very common question. Is going to involve like, okay, well, what if you had the option to do it with, if space wasn't an issue, how would you solve this problem? Oh, well, I'll dump everything into a hash map and then I'll just do a lookup. Is almost always the right answer to that question.
So, I mean, obviously, you speak on this much more knowledgeably than I do, and I feel like as a web dev, this does not come up very often. It comes up on Advent of Code because that's hey, here's a bunch of data, figure out the algorithm to get this answer. Now, what if that data was like 20 times larger than that? And you run into the Big O, because now you're like, okay, now that the data set has gotten much bigger, because that's basically what big O notation is. It's like trying to approximate how long something may take to figure out a problem as the argument n gets bigger.
Yeah, it's
Or
like
towards
the
infinity.
limit in math, right? It's like as the limit
Yeah.
increases,
Yeah.
as n goes to infinity, what does the function look like?
Right, but obviously you must use this kind of stuff a lot more than I do. So like, how do you use big O notation like on a daily basis in your programming?
Part of it is just shorthand, right? To discuss when we're discussing potential solutions to problems. I can say, well, you don't want to do that. That's going to run in quadratic time. We could do that better if we do it in n log n. So let's think about that, right? The main way is in like dissecting the algorithm or the code that you're looking at and identifying like where are the potential problem areas, right? If I see a triple for loop, I'm going to call that out like right away. Like at this point, it's more instinct than anything else. I've just been doing this so long. I see something like that and I'm like, red flag. And sometimes it's okay because like, no, this is in fact the best way. You know, we're not actually doing 3 full loops. Like this one's actually a little bit smaller. Or this one only goes through 2 times. And it's just, you know, for simplicity of syntax, we wrote it this way. So there's some discussion in design. There's some discussion in code review, like where these two where the big O notation comes up. Anytime you're talking about complexity or efficiency, it's going to come up. The main area I've seen it come up though is job interviews, because that is where I expect someone to be able to talk about this. Because if you're dealing with large data, if you're dealing with anything at scale, this is the kind of thing you need to know, right? You have to be able to analyze a piece of code and understand its complexity so that you can say basically whether or not it's efficient. And it also helps you identify where things can be done better, right? A lot of the times, the trade-off that we're making isn't space versus computational time. It's computational time versus developer time, right? It's going to take me a lot longer maybe to write this method in this way so that it's, you know, I can do it in this complicated way. And then, I'm going to do an in-place sort that's going to be really efficient somehow. So I'm not taking up any extra space. And then my lookup is just log n. Great. Okay. You know, that's a good thing. But that's going to be harder to read than like a double for loop. You look at a double for loop and you're like, okay, from 1 to 100, from 1 to 100, go do things. Great. So
are you saying that you would choose the double for loop for readability as long as you know the input is not going to get?
Yes.
Okay.
And again, if you graph these things, you know, I mean, it happens real fast, but they don't exactly. Linear might be better or it might be worse for a while than something else, right? Depending on the size of the input. But as it grows, again, as the limit goes to infinity, that's where it starts to matter. And so, yeah, knowing the size of your input helps you make intelligent choices about what algorithms to use. And then just knowing, like, okay, I know sort is going to be n log n, right? If I'm trying to do something that I need really quickly, I need to return an answer very quickly, I am probably not going to do a bunch of sorts, right? Maybe I'm going to take the sort out of that and I'm going to pre-process it, right? And I'm going to say, okay, let's put the data into this format so that we can look things up really quickly. And so like that's where that kind of trade-off can come into play. A lot of times for me personally in my own projects, I will knowingly implement the slow way, but I'll isolate it into like its own function so that I can optimize that piece later, but I can get the full logic. Because sometimes, especially with like advent of code problems, half the time is spent like trying to figure out what are they really asking me to do here.
Yeah.
And so like just validating your solution is a good way to go. And then you can say, okay, well, I took the quadratic part and put it over here so I can go optimize it. And I didn't even bother trying to put an exponential thing in. I knew that was going to take too long right off the bat, and so on.
Yeah, I understand I better understand now why you said that this is like the science of computer science. I mean, this is like the math of analyzing a problem. And also when you said that, you know, at a small input, so correct me if I'm wrong, but like at a small n, does that mean that an algorithm could be or just look like ON, but as it gets bigger, it looks like ON squared or something like that? Like, depending on your frame, how much you're showing, like, one algorithm could actually look like another one until you add enough input.
Right, because that's the thing. As it grows, it takes more and more time. So if you're doing like an operation on like a 10-element array, it almost doesn't matter because, you know, 10 squared is 100. That's not that much, right? If everything's like a microsecond or something in a nanosecond of time to each step, a human can't even tell that much time passed. But if it's like a second for each operation, you're going to notice the difference between 10 seconds and 100 seconds. And you're certainly going to notice the difference between 100 seconds and 1,000 seconds. Or whatever 2 to the 10th is, 1024 probably. So 1,000 basically. So that analysis, that ability to look at a problem and identify what is the big O of this, and B, is that okay given the data that I expect to have, is like the foundation of the science part of computer science, which is often very much overlooked in the engineering field.
Yeah, I mean, I feel like maybe if I worked at, Meta or Google and was working on big data, this would come up constantly. But because I'm, in my jobs, I'm never dealing with data sets that huge. And so it rarely, if ever, comes up, except kind of theoretically, like the data set is always so small, like you said, that it almost doesn't matter how I approach it. Yeah. It will do it in a fast enough time that you can't tell that it, how I did it.
Right. Well, the other place that this comes into play and why it's less relevant now than 25 years ago, although it is still relevant, is the speed of your computer, right? If you have very slow computer, like an embedded system, right? Those tend to not have as much computational power, like the set-top box in your machine or on your TV or whatever, right? Like that kind of thing, the embedded system on your car. Those are going to tend to not be as powerful as like your computer. And so a lot of the times for embedded systems or games where there's a ton of stuff that has to happen, that's also where you need to consider these kind of things. If you're doing, a 52 card deck, you probably don't need to worry about too much if it takes a little bit of time. And a lot of times developers will hide this stuff behind like animations and things.
No, I would never do such a thing. I spend more time using a set timeout in JavaScript to actually wait because I need to, artificially make something take a little bit longer so that it feels like something's happening. Like, it's almost like you said, computers are so fast sometimes that if something happens instantaneously, we actually are not sure that it did anything if we don't see some kind of processing, either a visual thing, a sound, time. So it's kind of interesting, because I was going to ask you, like, whether this big O notation, whether you think, whether it's more relevant and useful now than it was when you first started. And I was going to think the opposite. I was going to think that because data sets have gotten so much bigger and it's all going on the cloud and stuff, that this would be more important than it was 25 years ago when everything was in... Well, I guess that's the weird part, is that it was the cloud in the beginning. It came to our local computer. Now it's gone back to the cloud. So it was relevant, and then it became less relevant, and now it's becoming more relevant again.
Exactly. Well, and that's the thing, right? Is 25 years ago, this mattered because computers were slower, but we weren't dealing with as big a data sets in general. Now, computers are faster, so a lot of the problems that maybe I would have cared about this more 20 years ago, I don't care about, but there's problems with bigger sets of data. And with the bigger sets of data, you need to keep these kind of things in mind. And a lot of where this kind of stuff gets taken care of, like I was saying earlier, is in picking the right data structure to store the data in and picking the right algorithm, right? It's usually a combination of those things where you want to take the data, put it in a situation, into a format that you can access it quickly and efficiently so that you don't end up with these big times. Because if you're every single time that you want to look up something, you're processing all of the data, that gets slow really fast. But if the data only needs to be processed once, shove it over there. You're like, yeah, that part's quadratic, but I don't care because I do that once a year. And it runs in the background. It doesn't slow anybody down.
Is that like before we had rainbow tables and everybody was trying to figure out all these passwords underneath a certain character length? It took all the processing power, but then they basically made the hash map that they can just look up, which solved that big O issue.
Yeah. It's why I tend to gravitate towards hash maps for most of my problems, is because because reading tends to happen more often than writing, just in general in software. But there are absolutely problems where that is not the case. And then you need to make sure that you're using the right algorithm.
Right.
Because you can do any of these things. And if you have infinite time and infinite space, who cares? Right. But we don't. We don't have infinite time. We don't have infinite space. And I don't have infinite patience. So for me, everything in computer science is trade-offs.
Yeah. Well, I mean, that's kind of life, really.
Yeah.
You want to get super. Yeah. Okay. Well, I'm not even going to try to do. Okay, so this is what I know about ON now. Honestly, this is like the kind of thing that, besides the fact that I enjoy having it kind of taught to me by you, someone who understands it better. But it's also like there's so much good documentation for this online. Like this is the perfect kind of thing to go down like a wiki rabbit hole if you want to learn about computer science. This is just like one tiny branch of that whole field. But yeah, I mean, this was elucidating for me at least. So
and definitely know this stuff before you go for job interviews.
Yeah.
The closer you get to like a full software house, as opposed to like a lot of places you're doing software for a company that isn't like software-based company. It's just they need something written. They might not know this as much, but if you're going to work for like, one of the FANG companies, you're going to need to know this.
Yeah.
And it's just going to help you in general to be aware of how long things take to run.
Yeah. I totally agree. And I think that about does it for this episode on Big O notation. Thank you for all of that information, Matt. I appreciate it. And if you want to hear more discussions, including the P versus NP episode that Matt alluded to, which is very related to this, you can find those at hackingthegrepson.com. We will try to put out a new episode every other Wednesday. But until the next time you try to run an algorithm on a increasingly large data set, we return you to your regularly scheduled lives already in progress.